I put that signal in, and I get something out. Okay, and this thing here equals the impulse response. The response of the system to an impulse. Okay, obviously. So very simple, right? I have many different possible signals. I have to describe all possible outputs. But now I just need to focus on one particular output, this one. And if I have that, if I can get hooked to that too, then the Yn, now I can be able to describe the output of any other system, so any other signal. Then Yn, by definitions, then Yn here is by definition is output of the system to that. Then what would be? What would be? There's a convolution there, right? There's a convolution there. The Sn here is to be the convolutions of x. So I have an x curve here, and I have an h of n minus curve. The curve is about here, and that is a convolution. Okay. So we need to write that is x convolved with h in n. Okay, so let me repeat this theorem, and we will going to prove it. The theorem here says that S had to be an LTI, right? First had to be LTI, and LTI before makes sense. If it's an LTI, then all I have to do is recording H, which is impulse response. Then having that, I now can describe the system because its operation here, you can see that I can instruct my computer, if I know those H, and any X I put in, I can compute out. Okay? That's clear, everyone? Now this thing here is an extremely important statement. So imagine, right? So let me put you a real scenario now. Many people here use cell phone, right? So you use a cell phone, and I talk to someone. They're going to transmit through the radio link, right? And to the base station, and then transmit wirelessly. Now, and it is known that when I send that information wirelessly, they have a lot of trouble, right? You get to the one browse, right? You get the ceiling. So there's a lot of difficulty within that, right? And very different varieties. And then I have a signal down there. So you can see that I send a signal, I say something to go through the channel, this channel, and something comes out here. Now this channel here is something I cannot know beforehand. I cannot know beforehand. It's very hard to model, right? I cannot model my cell phone on all different setting combinations and so on. Very hard. So you see that you have a black box. And then I really need to know this thing because I put something in, something come out here very corrupted, and I need to know what the system has done to my original input so that I can undo the operation. Right? I need to know the system. You understand, right? Without the problem. So very hard. And one way to do that is I have to tell what I send, and I can tell describe the system, I have to tell the input and output. But that really defeats my purpose, right? But I only want to see this. I want to know what this is. Right? Can you see that? So now the communication channel, one thing people can do very simple is, based on this theorem, before you send any foreign information, you want to test the system, right? You simply send an impulse. You put them in, and let the other end record what's come out, right? And after the recorder come out for that one single input, you say, aha, now I know everything about the systems. Right? And I know everything, I know what is doing to my signal. And based on that, I can undo Now, given y, I can know what is the original x. So that's something you can see, right? What is the problem with that? What is the problem? Yes? The sum here, k here is just, let's say the integer from minus infinity to plus infinity. So the sum is k. Okay. Take all the k. Yeah, it's a good question. It's going to show exactly what is going on there. But the thing we want to capture here is, believe us here now. If I know x, I know x. I can compute y on every n. Right? A simple summation. So the example I just tell you earlier on about the systems. What is wrong with that? What is missing there? Excellent, very good, yes. The suggestion here is the summation here is good in the mathematical term, right? But we have infinite sum here. A computer cannot wait forever, right? You cannot wait a friend there and always wait, right? Let him just, compute this. You have a certain delays that you can tolerate, right? So, cause is way engineering fix is maybe you can truncate. If this thing going to decay here, going to be small very quickly, then it get ignored. Okay. So yes, we'll talk more and what truncation have to have impact in the overall system. Very good. What are the things? In my example, this communication channel, what are the things that we have to be aware of? I want you to take as an engineer designer the state of the systems, right? I put this thing here, maybe something come out here is very large and it might work the system. Very good. What else?
Causality.
Maybe
the causality.
The
causality.
The causality, yeah, okay, yes, the causality, yes, something important, yes. So maybe I want to compute this thing, but I cannot do something of x in the future. Yeah, that's exactly right. Yeah, I want to in the real-time system. What else?
I think it is very important when we have the linear time invariant system, because in my opinion, the signal, every signal can be a summation of the equal signals.
Yes.
So if we don't have the first property, we can use the summation of equals. So I think the most important is linear
time invariant. Okay. Yes. Yes. That's exactly the thing I'm looking for. The example I tell you earlier on that I can use this trick. That when I have an unknown channel, I want to find out about that channel, and I tell you the trick that all you have to do is just ask the other hand, send impulse, record the output, you know everything about the signal. Now that things only have to remember the theorem I said, it has to be an LTI system. The system you have can be assumed to be an LTI. Right? And that means you have this tool. And as someone just suggests, it is quite a strong condition. But the communication channel, let's say, what they do is they assume that, let's say, even in this room, the system quite the same. So it is going to be, linear time invariant system for that particular time. And maybe when you run to the other end, for example, you're going to send out the impulse and you're going to get another system. So the communication channel, regularly you have to update and try to find out what is the system, the new system at each time. Okay. Any other questions? Okay, so we have that. So now I want to also stress a point. It is very important for us to understand the theorem and proof. Right? As I tell you, I'm going to teach us in the graph.